Hello, and welcome to another one of my APES videos. This time we'll be looking at Chapter 9, Water Resources. Let's start off by saying that if you were an alien coming to Earth, looking at our resources, and you saw our surface, you'd go, wow, it's a lot of water you got there. They're doing really well in terms of how much water they have. Well, it's true, water is very abundant, but unfortunately, usable water is very rare. So, nearly 70% of the Earth is covered in water. Those aliens would see, we have so much water, but the problem is not much of it is fresh. 97% is in the oceans, 3% is in fresh water, a fourth of it is underground between all the sediment and things that are beneath their feet, and the rest is frozen in the glaciers. So, not much of it is something that we can use for our toilets and for washing our cars and drinking, because most of it is salty. So we'll get into that in a bit, but something that's interesting to think. So we'll talk about places where we would find this fresh water, but we'll start with the groundwater. Now there's a few places that water is stored in the ground, and they are specifically named because there are different structures underground that hold them in different ways, and so there are a few terms we need to get comfortable using. The first one is aquifer, water found underground in the tiny spaces between rock and sediment. On Long Island, we do in fact have aquifers, and I'll show you a picture of that in a bit, and that is where we have most of the drinking water stored from the last, long time of rain that has gotten its way into the ground and been stored there for a long time. An unconfined aquifer is when water can flow in and out and be recharged often, unconfined meaning that there are no layers around it, so there's easy access. But a confined aquifer has water that remains inside, and it has less influence from the outside. Usually there's a clay layer that lies over it, and so things from the top don't get down. That's why we say that there is less anthropogenic influence. Pollutants that would be running down with the water through all those sediments aren't going to have a nice time running through clay. Usually clay will help to catch some of those impurities, and by the time water actually drips through, it'll probably just be water. Lastly, we have the water table, the uppermost level at which the water in a given area fully saturates the rock or soil. So this is the top of where water actually is building up in the ground. It's a little bit easier to describe through picture, which again, we're going to get to in a moment. So here we have a few of those terms that are shown in this diagram. One thing I do want to point out that is always in these pictures, and I think needs to be said, is that if you see the blue, that does not mean that it is simply water. That is water that is fitting in between all of those sediments. So where it says the confined aquifer or the unconfined aquifer, don't think of that as being lake layers. And it's hard to draw this in diagrams, but don't think of that as lake layers. Think of that as layers of sand that are full of water. Like if you were to dig a hole at the beach, you know how sometimes you eventually dig down deep enough and you can start seeing water pooling up at the bottom? Well, that water was in between grains of sand. So you can think of it like that. Like all of these blue areas are areas that are where there would be airspace usually. There is water filling in the gaps. So with a confined aquifer, let's start with that at the bottom, you can see that it has that confining or impermeable layer above it. Impermeable meaning that water doesn't go through it, or not easily. Then the unconfined would be on top of that, and you can see that there's the home right next to it, there's the river that flows through it, so it does get access to water, so we don't call it confined. The water table is to the right of that, and you can see the arrow pointing to the top of that blue layer. Again, the blue layer is not simply all water, it's just where the top of the watery section of sand or sediment exists. Then you can see that there's a well that they're pumping into that unconfined aquifer, getting water pumped into their home. And you can also see the recharge area all the way on the left over there. That recharge area is showing the area where you can fill that confined aquifer. So the water has to get in there and be there somehow. It would be a recharge area, or sometimes they call it a recharge basin, where it does actually fill up. You can see that there is the upper glacial aquifer, which lies up on top. Then you can see underneath that we have the Magathie, which is quite thick and runs all the way from the Sound to the Atlantic and out quite a bit. Then we've got a clay layer, and that is over the Lloyd aquifer. So we have quite a few places where we have all those different, confined and unconfined layers, or aquifers rather, that supply our water. So when talking about water resources and showing you all these things with where we get our groundwater from, we do have to talk a little bit about wells and their effect on the water table itself. So the water table is the level at which the ground is full, right? You can say that water is up to a certain level beneath, usually a couple feet, could be deeper than that, beneath the surface. So with a well, if you're pumping water out, it makes sense that eventually that water table is going to be affected. And we do have pretty vigorous rains that come down in this area sometimes, and it refills and that water table shifts. But when you have heavy pumping and you haven't had a lot of rain, you can definitely get some issues. Here we're seeing a smaller effect of the wells, which is to say that if your well is pumping, it makes what we call this cone of depression, where you can see by the bottom of those two shorter wells, it is slurping up that water into the well, and you can see that the water table has dropped in that V shape. That's why we call it a cone, right? It's going down in a cone shape around where that well is taking water from. Now the issue with that is that if there is too much drainage from the area and it can't recharge, eventually you may have those shorter wells not actually catching any water. So if we have these houses that are by perhaps a farm, right? Maybe there's farmland that needs a lot of water and they're using a well to get it, you're going to have a huge cone if they require a lot of water. They're pumping a lot. And what you might find is that the two wells that were at one point getting water supplied by that water table, well, if the water tables dropped significantly from the other well, they might just go dry. And so this is an issue that people need to be aware of so that they don't run out of water and so that we can keep things kind of good between. Another issue that we can get, mostly along coasts, is saltwater intrusion. So where you have the land meeting the sea, there is an exchange of water. The fresh water that drops as rain is always trying to find its way back to the ocean, and we're familiar with that mostly through rivers, but that does also happen through the groundwater. So that water table is bringing that water, or showing where that water is dipping, right, because it's leaving the ground and going into the water, and you can see the flow going again from land to ocean. But there is an issue when you add a well to this equation. If you are in a coastal region and you have a well and it is pumping a good amount of water, you could end up with something called the saltwater intrusion, where you are actually introducing salt water back into the land because you're taking away water from that area. So you can see here it's directed the flow instead of out to the ocean. It is now directing it back into the land, and eventually your well could become a salty well, and nobody wants to be showering or drinking salt water. If the water doesn't end up in the groundwater, it may end up being surface water, or, in other words, end up being in a lake or river. In terms of lakes, lakes are formed by depressions in the landscape, tectonic activity, or glaciation. So glaciation actually led to the photo pictured below, which is a picture of Lake Ronkonkoma on Long Island. It's a pretty deep kettle lake formed by a piece of ice that had broken off from the last glaciation event and made this 60-foot or so deep kettle lake. In terms of the atmospheric water that we have, there's not really much up there. I mean, it is certainly important for global distribution. Rain is going to fall over various areas, and that's going to bring fresh water to places that otherwise would not get it at all. Agriculture, livestock, and nutrient cycling depend on rain to fall. Without rain falling, there's literally no new fresh water that's being brought to land. So, water is not very available. What can we do as humans to make it more available? The purpose of a levee is to keep a stream going in the same direction. Streams tend to meander and move, so if they can build up the sides of the banks, they can make it so it's not encroaching on the surrounding land. But what are the disadvantages of the levee? Well, it was probably at one point a very fertile place for agriculture, but because you're stopping the flooding by putting these banks, you are not going to be adding to the fertility of that floodplains. Sediments get deposited where the river meets the ocean instead of on the banks and building up the land. Levees prevent flooding in one area but increase it in another, so you're making this river continue to shoot straight instead of meandering and slowing down and eventually building up in one area or another. So there's going to be flooding of that water somewhere else. And it also encourages development on the floodplains. But if you're having new houses come to these floodplains and building up, well, if the area floods, they're not going to be very happy. The next way that humans deal with water is with dikes. So they are similar to levees in concept, right? They are preventing water from coming into a certain part of land, but instead they are preventing the ocean water from flooding the adjacent land. The Netherlands is below sea level, so they have to have an entire extensive system of dikes to make sure that they're not flooded. The next one we are all familiar with, the dam. It is a barrier across water, usually a large river or stream. The water is stored behind a dam in a large body of water called a reservoir. So that's the giant lake that builds up behind the dam. They are built for human consumption, generation of electricity, flood control, and recreation. So they're not just for electricity, they are for many different things. There's over 82,000 dams in the United States, ranging in sizes from really small, maybe a smaller stream, to pretty big. Only 3% of the dams in the US were built for hydroelectric power, 18% for flood control, 38% for human recreation. We'll see some different sizes so you can get an idea of what dams look like. So here in this picture is the Hoover Dam, which is an example of a quite large dam. This would be an example of a much smaller dam, and it is nowhere near as massive in scale and size. It's probably not making much of a reservoir behind it, but it is blocking water and controlling its flow downstream. So what are the disadvantages of dams? A large amount of materials and energy are required for these things to be built. They are structures that need a lot of support, a lot of concrete and such, so that they can block that amount of water. They need to be strong and they need to be reliable. They displace people from different areas. If you're building up that reservoir behind it, any of that land is going to get filled in with water, and if there were people, they've got to go somewhere. Disrupts natural seasonal flooding, so downstream where this building or this dam is, it is going to be making it so that the water coming out is very regular, right? It is a constant, not really a flooding flow. So it's going to make it so that there is no seasonal flooding downstream. That interrupts the natural flow of water, and it's also going to heavily displace migratory fish such as salmon, though they have come up with a way to deal with that issue, which are fish ladders, which are ways that the fish can actually swim up the side of the dam with water and steps. There are some different ways to do it, but eventually the fish do get into the reservoir up top so that they can spawn. The last way that humans interact with their water resources, or at least to get water, is through aqueducts, which are canals or ditches that are used to carry water from one location to another. And it's not the most efficient thing. The water is evaporated as it travels from one spot to another, and the water can travel a pretty long distance to get to its destination. So New York City has millions of people that live there, and they are surrounded by the salt water of that island. So where does all their fresh water come from? Well, the answer is it comes from the West Delaware Tunnel. I know it's not the best resolution picture, but West Delaware Tunnel and the East Delaware Tunnel coming from this area, going all the way through the Delaware Aqueduct and also through the Catskill Aqueduct coming from the mountains to the north. So there are two aqueducts that bring water down, and this is actually a 2-slide picture, so bear with me for a moment here. And if you follow that down, these two aqueducts come into the area right over here for Queens and Brooklyn and Staten Island and New York City. So that is where all of their water comes from, all the way up north, a couple hundred miles through these aqueducts, through these tunnels. LA has a similar situation where they have the California Aqueduct and the Los Angeles Aqueduct that both move that water south into Los Angeles. And again, that area, it has many people in it, and they need to get water somehow. And there is not enough fresh water in their groundwater to support them. So they need to take water from these other places and meet the demands of their people. So what are the disadvantages of aqueducts? Well, it takes a lot of time, a lot of money, and a lot of resources to pipe water from one place all the way to another place. This disturbs the natural habitats and fragments habitats, right? You have a tunnel or a pipe that's going through a forest, it's going to break it right in half. Less water is flowing to where it naturally was before. If you're taking it from one place, bringing it to New York City, well, that whole area gets less than what it had. And then ocean water will flow into river mouths that have less water flow due to aqueducts. So the river usually was spilling out into the salty other place, and perhaps it was brackish, right? A mix of salt and fresh water. Now maybe you have more of like almost like a saltwater intrusion happening there, where it will move in, and that could disrupt a whole bunch of fish species, intertidal species, a whole bunch of different things that live in that area that aren't used to getting that much salt. So, not the best plan. So I've got an idea, said someone once upon a time. Why don't we just take all of this water that has salt in it and take the salt out? And that is something that we are attempting to do, but it is difficult. We call the process desalinization, the removal of salt and everything else that's in ocean water, from ocean water. So hopefully that we can make fresh water out of these places where we don't have accessible water naturally. Countries in the Middle East produce 50% of the world's desalinated water, mostly because of dependency. They need fresh water, and they're not getting as much rain as other areas. So they definitely need to work on those technologies to meet the needs of their people. There are two different ways that we have desalinization, and we're going to take a look at those right now. So the first method is distillation. Heat is used to boil water, which leaves salt behind as it evaporates. If you have a cup of salt water and you just let the water evaporate out, you're left with a cup of salt. So the idea is that if you can capture that steam, if you can actually get the water that evaporates to condense, turn back into water, you're going to get fresh water from that. So that is the idea. The only problem is a great deal of energy is used to boil that water so that they can get it to evaporate and then condense later. So not the most energy efficient process. This picture looks pretty complicated, but really it's not as bad as it seems. If you follow the numbers as I go through them, you'll see exactly where all these things fit together. So seawater, again salty water, flows into the chamber. So that goes through that condensing coil first, right? It's coming through at 1, and the heating element boils water, creating steam. So it gets through, goes into that bottom chamber on the right, and you've got a heating element at the bottom that's going to cause it to make steam. Now remember, you've got seawater flowing through that condensing coil, so it's colder, right? It's not really warm. So what happens is the cool seawater in that condensing coil causes that steam that was just made to condense, form into regular pure water droplets. And so the salt-free water at 4 is going to flow out of the chamber after it's collected. And then 5, the brine, or the very salty water, which will be extremely salty since you're taking most of the water out, will flow out, and they have to deal with whatever's left. So that's the idea, that they're heating up the seawater, they're catching all of that vapor, and then they're taking that away as fresh water by using a pretty smart process of cooling it using the seawater itself. The second process that they use is something called reverse osmosis. So water is forced through a thin, semi-permeable membrane at high pressure. This means that it's almost like a screen. You're like pushing this salt water against a screen, and you're going to get the salt stuck behind and the water going through. That's the idea. So here we have another numbered diagram. Number 1, seawater flows into that chamber. 2, the pressure is applied to the water, so it's pushed against that semi-permeable membrane. Under pressure, water is pushed through, and salt cannot make its way through, but water can. Water is a smaller molecule than the salt, so it is going to be able to be pushed, but it does take a lot of pressure to separate the two from each other. The salt-free water flows out of the chamber at 4, and then again you're left with that brine, that very salty water that you have to deal with somehow. So, humans need a lot of water, but what are they doing with it? Well, 70% of the water that we take from the fresh water that we can is, 70% is for agriculture. 30% is then split between industrial and household uses, and that depends on where you are. So water usage varies greatly among countries, depending on how much industrialization there is, depending on the different household appliances that are used. If you're in a place where you don't own a car, you're not going to be washing your car, so it can vary quite a bit. But again, 70% is used for agriculture. That's the primary thing that we need all this water for. So here is an image of the total per capita water use per day in liters. So the United States has just almost about 7,000 liters used per day per capita across the whole spectrum, and we are definitely the leader in that, followed by Spain and then Canada and France and so on and so forth. But we definitely use a lot of water per day as a country. Going back to agriculture, irrigation plays a big part in how much water, and it is the greatest potential thing for conserving the water that they use on a regular basis. So the first way we're going to look at irrigation is furrow irrigation. It's easy and inexpensive. All they do is they make trenches or furrows along the side of their crops, and it is approximately 65% efficient. So 65% of the water that they put in is actually making its way into the ground, into the crops, and not evaporating. So this is what that looks like, and you can see that there's that tube, and it just spills out water in the different rows of all their crops, making those little furrows or little areas for the stream to go. The next type we have is flood irrigation. So flooding the entire field, letting the water soak in. It's a little bit more disruptive. Plants don't like to be totally drowned. They like a little bit of air and a little bit of water in their roots, but it is more efficient in terms of the water that they can put down, and so it's a little bit better than the furrows, but not by much. And it definitely has that cost of, well, you might disrupt the actual plant growth. So here's a quick picture of what that might look like. Just totally flooding a field, not continuously or for a long period of time, but just to cover that ground, make sure everything gets its water, and it will sink in and get its way to all of those crops. The next way that irrigation can be done is through spray irrigation. It's a little bit more expensive. It uses energy in order to spray the water. Water is pumped from a well, and it is generally pretty efficient, 70 to 95%, depending on what kind of pump or rather what kind of spray and how long they're spraying for. But definitely it is a little bit more efficient than the first. And so here you can see the sprinkler system going, probably like you've seen in your own front yard, right? The sprinklers going and spraying in different areas, making sure that they hit the crops, but not for too long. The last type and the most efficient type of irrigation is the drip irrigation. You have a hose that runs by your crops, and it slowly drips, 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 drips. Reduces weed growth because there is no surface watering. You're directly watering these drips onto the plants themselves, and again, it is very efficient with over 95% if you do it right. So here you can see that this hose is directly next to the plant, just letting that little stream, that little drip go. You can see here that there is no other growth in between the plants, right? It does not let weeds grow because the rest of the ground is totally dry. You're only hitting specific spots, and that also means that you're conserving water. You're not spraying all this dirt that isn't growing anything. So that is the thing that makes it so efficient. Now there is an alternative to all this. Instead of farming outside, why don't you farm inside? Well, that's what a few people have tried to do and are currently working on. Growing crops in a greenhouse with no soil, just a nutrient-rich solution, and it saves a lot of water, up to 95% less water used because you're not spraying it around and having it evaporate. It is a very controlled environment, and so it can hit exactly what you need it to hit and isn't going to be lost to the atmosphere. So this is what something like that would look like. You've got these different rows being fed that nutrient solution, and they don't need to grow in soil outside. You can get these in very like industrial looking row and be pretty productive.